everyone. Welcome back to the lectures on Introduction to Multi-Agent Systems. Today's lecture will be a sort of a recap of some of the things that we've already discussed and also of some of the preliminary results which will be useful in proving the solution or in deriving the solution of the Laplacian flows for the case of undirected networks. To be a bit more precise, in the case of undirected networks, the Laplacian matrix turns out to be a symmetric matrix. Then what are the nice properties that we can associate with the symmetric matrix? Especially, what are the nice spectral properties which we can associate with it? Which will be discussed in today's lecture. So let's get started.
Let's start by looking at those properties of real symmetric matrices, which we'll actually be using to solve the Laplacian flows or to arrive at the solution for Laplacian flows. So today's lecture will be a quick recap. Now, for any real symmetric matrix, A, the following properties hold. The first property being all the eigenvalues of A are real or real valued, meaning lambda I belongs to R for every I going from 1 to n, where n the second property says that the eigenvectors associated with distinct eigenvalues of A are orthogonal to each other. So these are the two properties of real symmetric matrices that are going to be very useful for us. So let us see how we can prove them. The proofs of both the properties are actually quite straightforward. Let's start with the first one. Let us consider an eigenpair lambda v. Then we know that obviously the eigenpair satisfies AV equals lambda v. We now start the manipulations. Let us take a complex conjugate on both sides. Conjugate transpose on both sides. Then we would have lambda is a scalar, so it can be taken out and this. Notice that the conjugate transpose of A being a real matrix, is simply equal to A transpose. Further, remember that A is a symmetric matrix, so again, this becomes equal to A itself. Secondly, lambda is a scalar, hence its conjugate transpose is simply equal to its conjugate. We now use both of these results in this expression. What do we get? We conjugate transpose A is simply lambda conjugate times V conjugate transpose. Let us now do something else. Let us multiply V on both sides of this equation. So now we are using this expression, and to this expression, we are multiplying V on both sides. So this becomes equal to, we know that AV equals lambda V. We substitute that here and write V conjugate lambda V, V conjugate transpose, sorry. This lambda conjugate V conjugate transpose V. We can take lambda out, and this is what we are left with. So when does this equality hold? For this equality to hold, is it mandatory that lambda and lambda conjugate must be the same? Not really. We need to prove something for that. Because this equality can also hold when lambda and lambda conjugate take different values, and V conjugate transpose V is equal to 0. Meaning, if we want to prove that lambda is equal to lambda conjugate, we must first show that V conjugate transpose V is not 0. And the answer is, this is certainly not 0, as V is a non-zero vector. Why is V a non-zero vector? Because it's an eigenvector, and by definition, an eigenvector cannot be a zero vector. So the only way this property can hold is if lambda is equal to lambda conjugate, meaning lambda is real valued. Since we started with any arbitrary eigenpair AV lambda V and proved that lambda is real valued, this property holds for all of the eigenvalues. Hence, this is how we can show that all of the eigenvalues of a real symmetric matrix are in fact real. So now we look at the proof of the second property. For this, consider the eigenvectors V1 and V2 associated with distinct eigenvalues lambda 1 and lambda 2. Since it is distinct, obviously lambda 2 is not equal to lambda 1, respectively. Hence, we now know that the properties which hold are AV1 equals lambda 1 V1 and AV2 equals lambda 2 V2. Let us try to compute the expression or simplify the expression V1 transpose AV2 using just these two and the fact that A is a symmetric matrix. So obviously AV2 is equal to lambda 2 V2. So we write that here. V1 transpose lambda 2 V2. Hence we can take lambda 2 out and write V1 transpose V2. Interestingly, there is yet another way using which we can simplify this term. How can we do that? Let's see. Now the first term here can be simplified as A transpose V1 and then the whole transpose of it times V2. Remember that the matrix A that is given to us is a symmetric matrix, meaning A transpose simply equals A. So this becomes equal to AV1 the whole transpose V2, and this becomes equal to lambda 1 V1 transpose V2. So AV1 is equal to lambda 1 V1. That's how we write this. So now for this term V1 transpose AV2, we actually have two different simplifications, which are obviously equal. So we can write lambda 2 V1 transpose V2 is equal to lambda 1 V1 transpose V2. We can bring everything to the LHS to have V1 transpose V2 going to 0. Notice here that lambda 1 and lambda 2 are not equal, meaning obviously lambda 2 minus lambda 1 is not equal to 0. So then, when does this expression evaluate to 0? It evaluates to 0 now only when V1 transpose V2 is equal to 0. So the only way this works is when V1 transpose V2 is equal to 0, which implies that V1 and V2 are orthogonal to each other. We started with any distinct eigenvalues lambda 1 and lambda 2 and showed that their corresponding eigenvectors V1 and V2 are actually orthogonal. So what happens in the case of repeated eigenvalues? Well, suppose there's an eigenvalue lambda which is repeated, then it has an eigenspace which has a dimension greater than 1. Since we get the entire eigenspace, we can obviously choose its basis vectors to be orthogonal to each other. Meaning, we can select all of the eigenvectors of a symmetric matrix, whether repeated or not, such that they're all orthogonal to each other. Let us now see an example of a symmetric matrix. For the matrix given here, obviously A equals A transpose, meaning it's a symmetric matrix. And A, all the entries are also real valued, meaning the properties which we discussed just now about the eigenvalues being all real and the eigenvectors being orthogonal to each other must hold. So let's start by calculating the eigenvalues. So the eigenvalues can be calculated using determinant of lambda I minus A equals 0, which would give us lambda being equal to 3, 6, 8. I'm not showing the calculations here, but I encourage the students to pause the video here and do the calculation by themselves and see if they're getting these to be the eigenvalues or not. Similarly, the eigenvectors can be calculated using the expression AV equals lambda V. If we solve this, then, so what do? We just substitute different eigenvalues here. And for each eigenvalue, we get a set of linear equations. We solve them to get the corresponding eigenvector. So when we do that exercise, the eigenvectors turn out to be, the first one is this. The second one is, and this is the last one. So the question now is, are these eigenvectors actually orthogonal to each other? Let's verify that. When we do V transpose V2, we get minus 1 times 2. So this evaluates to V1 transpose V2 adding up to 0. In the same way, we can show that V1 transpose V3 also is 0 and V2 transpose V3 is also equal to 0, meaning we have in fact verified that all of the eigenvectors are actually orthogonal to each other. Now, when we are interested in arriving at the Jordan decomposition or the spectral decomposition of the symmetric matrix, then we further require the eigenvectors to be orthonormal to each other. But before that, let us quickly see yet another interesting property. Suppose we pick any of these eigenvectors which satisfy the property AVI equals lambda I times VI. Let us take a transpose on both sides. This gives VI transpose A transpose. Lambda I is a scalar, so it just stays as is, and VI transpose. But A is a symmetric matrix, hence this expression gets simplified to VI transpose A. Let me write it here. This implies VI transpose A is equal to lambda I VI transpose, meaning VI is both the left and right eigenvectors. They can be selected as the same in the case of symmetric matrices. Is the left and right eigenvector is a candidate for it. So when we are doing the Jordan decomposition, however, we have to make sure that some other properties also hold. That is, we have to use orthonormal vectors in that case. Let us try to convert these into orthonormal vectors. How can we do that? So these are simply orthogonal. But now we want to have orthonormal vectors. And all that we have to do is we have to make sure that the norm of every vector is 1. Hence, this is how we convert V1, and obviously this is V2 and this is V3. So notice here that the norm of each of the vectors now becomes equal to 1. Furthermore, let us construct the vector, the matrix now, consisting of V1, V2, and V3, which are the normalized vectors, as its columns. Then what can we say? We can quite easily see that V inverse is equal to V transpose, meaning this is simply an orthogonal vector. Orthogonal matrix, sorry. Additionally, the Jordan decomposition of A can now be done using the matrix V and is given as Vj V transpose, where J turns out to be a diagonal matrix when we are using, it's a diagonal matrix when A is a real symmetric matrix, meaning real symmetric matrix can also be diagonalized. It can always be diagonalized. Okay, so these are all the properties that we will need to arrive at the solution of the Laplacian flows. So with this, I'll end today's lecture. In the next lecture, we'll see how we can actually use these properties. Okay, thank you.